In this video we're going to go over Kirchhoff's rules and how to apply them to solve problems involving more complicated circuits. So the first rule is called the loop rule, and it says if we go around a loop, and the loop is any closed path within a circuit. For example, if we start at A and go around the circuit until we come back to A, that would be a loop. So the loop rule says that if we go around the loop and we add up all the changes in electric potential that occur, then the sum of the changes in electric potential will be 0. And this is because the electric potential at a single point can only have one value. So if the changes in electric potential as we went around the loop were not equal to 0, that would mean the potential at A has two different values, which doesn't make sense. So when applying this rule, we have some rules to follow to determine the sign of the electric potential change. So the first is for batteries. So before you apply the loop rule, you have to determine which direction the current is moving in, and then also pick a direction to move around the loop. So once you do that, if you have a battery and you go from the negative to positive terminal, the change in potential is positive, because remember, a battery does work on charged particles to move them from the negative to positive terminal. So it will increase the energy of the circuit. So then, if we move from the positive to negative terminal of a battery, we say the electric potential change is negative. Now, for resistors, it depends on which way the current is moving. If we go around the loop in the same direction as the current, then when we cross a resistor, the change in potential will be negative, because the resistor is taking away energy from the circuit. So then, if we are moving in the opposite direction as the current across a resistor, the change in potential will be positive. So let's apply the loop rule to this circuit. So we start at A, we choose the direction of the current to be clockwise, and we choose to move around the loop clockwise also. So the first change is this battery. Now since we're moving from the negative to positive terminal, the change in potential will be positive. So it will be plus 10 volts as we move across this battery. Next we encounter a resistor, and since we're moving in the same direction as the current, the change in potential will be negative. And so from Ohm's law, we get that the change in potential across this resistor is equal to the current times the resistance. So the change in potential as we go across this resistor is minus 20, which is the resistance, times I, the current. And we don't know the current yet. The next change we encounter is this battery. Now, in this battery, we're moving from the positive to negative terminal, so the change in potential is negative. So we lose 4 volts. And then we have 2 more resistors, and again, the potential difference as we cross them will be negative I times the resistance. So once we have, and then we come back to A. So then we have all of these changes in potential, and we know that they have to add up to 0. So using this equation, we can solve for I, the current, and we get that the current is 0.05 amperes. And so the original question was to find the potential difference between points A and B. And to do that, all we have to do is start at A and then add up the potential differences as we move to B. So the first one is the battery. Again, this is positive 10 volts. since we're moving from the negative to positive terminal. Next we have the resistor, and the potential change as we go across the resistor is minus 20, which is the resistance, times the current. And so now that we know the current, we can plug in for I. So we get the potential difference between A and B is 10 minus 20 times 0.05. So overall it's positive 9 volts. So point B is 9 volts higher in potential than point A. So up until now we've assumed that the voltage difference across a battery is equal to the EMF. But in real batteries, they have internal resistance. So when a current is present, the actual potential difference across the terminals of the battery is less than the EMF. So we represent a battery with internal resistance in a circuit diagram with this little resistor next to the battery. And so for a battery with internal resistance, the voltage difference across it is the EMF minus the current times the internal resistance. So when there's no current, then the potential difference is just equal to the EMF. The second of Kirchhoff's rules is the junction rule, which says that the total current entering a junction, which is just when the wire splits off, so the current entering the junction is equal to the current leaving the junction. And this is because electric charge cannot be created or destroyed. So the current can't just disappear. It has to be split up. So here, the current entering the junction is I, and then the two currents leaving it are I1 and I2. So we know that I is equal to I1 plus I2, because the current can't just disappear or appear out of nowhere. So if we connect the terminals of a battery with a wire that has zero resistance, then it results in something called a short circuit, which can burn the wire and destroy the battery. Because from Ohm's law, we see that the current is equal to the EMF divided by the total resistance, which is the resistance of all the resistors in the circuit plus the internal resistance. And so since we only have a wire with zero resistance and no resistors, the big R is 0. And so if our internal resistance of the battery is very small, then you can see that the current will be very large, which is why it's so dangerous. So you always need a resistor in a circuit to prevent this short circuit. Next we're going to be looking at the equivalent resistance of different connections of resistors. So equivalent resistance is basically if we have a group of resistors, like here, we can replace them with a single resistor, and the resistance of this replacement resistor is called the equivalent resistance. So if we have resistors connected in series, as we do here, then the current through each resistor is the same, and the equivalent resistance is just the individual resistances added up. So we can replace these three resistors with a single resistor, and the resistance of this single resistor will be R1 plus R2 plus R3. Now, if we have resistors connected in parallel, then the current through each resistor is not necessarily the same, but the potential difference across each resistor is the same. And so, to find the equivalent resistance, we use this equation. So Next we're going to look at some examples of applying these rules. So we want to determine the currents in each branch of the circuit. So we have I1, which is going around in this upper half of this part, and then I2 is going along this line, and then I3 is in this bottom half. So first, before we apply the loop rule, we need to choose a direction for the current. So we basically guess the direction, and then we can apply the loop rule. And we actually need to apply the loop rule multiple times in this problem, because we have 3 unknown currents. So first we take this bottom loop. So we start at B and we move clockwise. First we encounter this battery, and we're moving from the negative to positive terminal, so the change in potential will be positive 3 volts. And then we go around here and we encounter this resistor, so the change in potential across this will be minus the current times the resistance, so negative 18 I2, and these changes equal to 0. So we can solve for I2, which is 0.17 amperes. Next we want to do the whole loop around this whole outside of the circuit. So we start at B, and this time we're going to be moving counterclockwise. So first we encounter this internal resistance of the battery. So we're moving in the same direction as this current I1, so the change in potential will be negative, and it will be negative 2I1. And then we move across this battery from the negative to positive terminal, so again the change in potential is positive 9 volts. And then we have this resistor, so the change in potential across this is minus I1 times 12. And then we move down this way and we get to this battery, so the change in potential across this battery will be negative, since we're moving from the positive to negative terminal. So and then all these changes add up to 0. So we can solve that I1 is equal to 0.43 amperes. And then, so the last unknown current is I3. And to get I3, we can just use the junction rule at this junction A. So the currents entering the junction are I1 and I3, and the currents leaving the junction is I2. So I1 plus I3 has to be equal to I2. And since we already know I1 and I2, we can just solve for I3, which turns out to be negative 0.26 amperes. Now since I3 is negative, that means our initial guess for its direction is actually wrong. So I3 actually moves in this way, but the magnitude of this current is still correct. Next we're going to use equivalent resistors to simplify this circuit. So we want to find the current in this circuit. And to do that, we're going to basically replace all of these resistors with a single resistor. So first we start with these 2 parallel resistors. We want to replace them with a single resistor, and to do that we need to calculate the equivalent resistance. So for parallel resistors, the equivalent resistance is given by this equation. So we find that the equivalent resistance is 2 ohms. So we can replace these 2 parallel resistors with this single one that has a resistance of 2 ohms. So now we just have 3 resistors in series, and so we can replace all of them with 1 resistor. And remember, when we have resistors in series, to find the equivalent resistance, we just add up all the individual resistances. So we can replace these 3 resistors with one resistor that has a resistance of 15 ohms. And now it's very simple to solve for the current. We just use Ohm's law. So the current is equal to the potential difference, which is just the EMF, since there is no internal resistance of this battery, divided by the resistance, which is 15 ohms. So the current is 0.8 amperes.